Okay, folks, so for this screencast, this is a response video for Human Ross, who essentially said, can you solve a nonlinear elliptic PDE with finite difference? And here is the equation that he posted, u double prime of x minus u prime of x plus u, and honestly, this is kind of typed in by hand. It's really... I thought he posted a link. Here it is, the equation. Yeah, here's host math. There you go. So u double prime of x minus u prime of x plus u squared equals cosine squared x minus sine x plus cosine x. So the way I had originally intended to do this was this code here, and so I'm just going to walk through this because this method actually ended up not working, and so I just want to talk about this real quick. If you want, just skip ahead to minute. I'll put a time here. Skip ahead to this time here, and you can see the actual solution that works. So I'm going to put this in debug mode, and so basically, here's our function: u double prime minus u prime plus u squared equals cosine x. So all of this is really just a forcing function, f of x. So it really doesn't matter what it is. So what I did was I first discretized the bar into 1,000 elements. Made the bar 10. Here's my x vector. I grabbed dx, which is x of 2 minus x of 1. So my dx in this case is 0.01. And then here's f of x. And then here's the actual solution. I think Human Ross posted that the exact solution was cosine x here. It doesn't matter. He posted it somewhere. And so what I wanted to do is I just wanted to make sure this was right. So what I did was I actually did, here's the approximation to the second derivative, u of I dx plus 1 minus 2 u of I dx plus u of I dx minus 1 over dx squared. And then here's the first derivative, u of I dx plus 1 minus u of I dx minus 1 over 2 delta x. This is central differencing here, and this is the second order derivative approximation here. So I'm going to put a debug point here, hit continue, and then the approximation to the function f is essentially the second derivative minus the first derivative plus u squared, which is just this equation here. And if this is the actual solution, this approximation should equal f. So then I go ahead and I plotted some stuff here, and so there should be a plot here. Boom. So you see that the two curves match up perfectly. So then that means that negative cosine x is correct. Okay, so then the issue with the finite difference method is the fact that there's a ui squared here. So typically what you would do is you would solve for ui and then do like a Gauss-Seidel method or a simple fixed point iteration method or something like that. But because you have a ui squared here, you can't do that. If you solve for ui plus 1, you're going to end up, when I is equal to 0, you're going to have u1 equals ui minus 1, and then ui minus 1 is going to be u of negative 1, which doesn't exist. And so if you start at I equals 1, then you're never going to be able to solve for u of I, and then you're going to have one data point missing, which I guess conceivably would be okay, but I never tried it that way. So then the idea that I had was, let's solve it in this format where we have 2dx cubed ui squared minus 4dx ui plus 2dx ui plus 1, 2dx ui minus 1. And so basically what I did was I substituted in these two equations into here to get the finite difference approximation, and then put it in this form. And then the form that you end up getting is all of this is a variable called c. So here's 2dx u I dx plus 1, 2dx u of I dx minus 1 minus dx squared, u of I dx plus 1 minus u of I dx minus 1 minus 2dx cubed of f. And remember, f we defined up here. And then you say that a is 2dx cubed, here's a, and this is b minus 4dx. And what I did was I said u test equals a times u of I dx squared, which is this, plus b, here's the b term, times u of I dx plus c. And if this is right, this should all equal 0. And so I ran through here, hit continue. Whoop. Oh, I did not want to do that. How do I step out? Step out. Okay, good. Here we go. So then, did I plot that? So then there should be another plot. Here you go. And so here is the test that I did. It should be 0, and it is. And so the algorithm that I tried to do, I think this is getting kind of long. I think I'm just going to post this as a separate video. So I won't put that link up there. Forget it. Anyway, so here I plot U actual. I guess no labels aren't there yet. Hold on. Add the labels. So here is the actual solution to U of x. And then so my idea is to get U approx. Here's where I make the boundary conditions here. So in here I just make a copy U approx, and then I save the boundary conditions. And then I iterate 10,000 times, and what I'm trying to do is do this like simple fixed iteration thing, where essentially I have a of ui squared plus b ui plus ci equals 0, and then I use the equation above to solve for U approx. But I ended up having to do this weird thing where I had to make sure that the solution was real, and then I had to find the solution that was closer to the other one. And if you want, you can look at it and try to see what happens, but essentially when you finally run through this and hit continue, it looks like it takes a long time to iterate it 1,000 to 10,000 times. Yeah, wow, that's taken quite a bit of time. I wonder if running in I bet you running in debug mode is no good. I'm gonna quit. Uh-oh, I think I crashed my computer. I'm gonna pause this for a sec. Okay, there we go. Yeah, it just had trouble. What's it called? Yeah, it had trouble doing it in debug mode. But anyway, here's a numerical solution, and the boundary conditions are correct because those never change, but it never quite converges onto the solution, and I didn't really like this method anyway. It just, I just didn't like it. I'm curious to see if this would do it. Okay, that's gonna blow up. All right. Okay, so anyway, this method I didn't like, so I ended up doing a different method where I use RK4 and I blend it from the left and the right. And so I'll post a link to that here and in the comments below. But basically, this is just a follow-up video saying that the standard way to solve a finite difference method using linear techniques does not work, unfortunately, and you have to do something else. Okay? Great.